Okay, so think about this for a second. How can we actually truly trust the machines all around us? From giant factory robots to the rides at an amusement park. So often, our safety comes down to a single button or a single sensor just working. But what happens if it doesn't? What if that one crucial part fails? Well, that's exactly what we're going to dive into. Right. Picture a huge industrial press. The only thing keeping it safe is one emergency stop button. Now, if the wiring on that button gets frayed or maybe a contact inside gets stuck, the machine has no idea it's supposed to stop. It just keeps on going. That is a disaster waiting to happen. So how in the world do you protect against a failure you can't even see? And this right here, this is the whole game. On the one hand, a single sensor is a total gamble. It could break, and you'd have no clue until it's way too late. But with a redundant pair, the system is constantly checking up on itself. It's like it's asking, hey, are you okay over there? And if one signal doesn't match the other, bam, it knows instantly that something's wrong. This simple idea of self-checking is how you get to the absolute highest safety ratings in the industry. So this brings us to the core principle of modern machine safety. It's not just about making parts stronger anymore. It's about building them smarter. It's about giving them a backup. By taking two separate signals from the very same safety device, we create a system that is smart enough to catch its own mistakes. Now, the official name for this is dual-channel monitoring. It sounds fancy, but it's really a beautiful, simple idea with a huge promise. Two is always, always safer than one. Instead of one phone line, you've got two, and for the machine to get the green light, they both have to be saying the exact same thing. Okay, so how do you actually manage all this constant cross-checking inside the machine's brain? The controller. Well, you need a specialized tool for that. So let's meet the star of our show today, the redundant input instruction, or just RIN for short. And here it is. This little block of logic is our digital watchdog. Seriously, its entire job, 24/7, is to watch two signals coming from a safety button and to start barking the second they don't agree. This is the code that enforces the rules and keeps everything in check. And here's the most important part. The RNI instruction is a certified safety function. This isn't just some clever piece of code someone whipped up. It has been designed and tested and pushed to its limits specifically to do one thing really, really well: compare two signals and verify that a safety device is working perfectly. So its job really boils down to four key things. First, it's always watching two inputs, which we'll call channel A and channel B. Second, it's actively hunting for any kind of mismatch. That's called a discrepancy. Third, and this is crucial, if it finds one, it immediately traps the entire system in a safe state. And finally, it absolutely will not allow a restart until a human operator follows a very specific, deliberate procedure. So how does this digital watchdog actually, think? What's going on inside that little block of code from one moment to the next? Let's break it down. It's really just a simple, super fast, four-step loop. Step 1, it reads the state of both channels. Step 2, it compares them to see if they match up. Step 3, and this is so important, it checks the timing. When one signal changes, the other one has to change almost instantly too. And then step 4, only if everything is absolutely perfect does it give the all clear for the machine to run. Now, this watchdog can be set up in two main ways. In equivalent mode, it expects both signals to be on at the same time. Think of it like two identical switches being pressed together. But in complementary mode, it gets even smarter. It expects one signal to be on and the other to be off. This setup is way more robust because it can detect tricky wiring problems that the other mode might miss. So how much time does that second signal have to catch up with the first one? Well, by default, the watchdog gives it just 500 milliseconds. That's half a second. It's called the discrepancy time. It's this tiny little window, just enough time to ignore tiny physical jitters in a switch, but short enough to catch a real problem almost instantly. All right, but what happens when that 500 millisecond window slams shut and the signals still don't match? What happens when our trusty watchdog finally sniffs out a real problem? The moment that mismatch lasts longer than the discrepancy time, well, everything changes. The system immediately flags a fault. And the chain reaction is instantaneous. First, the RIN's main safety output just shuts off. That immediately cuts power to motors, valves, anything that could possibly be dangerous, and the whole machine goes into a safe state. And here's the key. The output is now trapped. It's locked out. Plus, a specific fault code is generated, leaving a breadcrumb trail for the technician.
And this right here is probably the most important rule of all. The system will not restart by itself. Nope, not going to happen. Even if that broken wire suddenly makes a good connection again, it's too late. The system is locked down for safety, and it's going to stay that way until a person intervenes. It puts safety above everything else. So the machine is stopped, and it's safe. Now what? Well, this is where a technician steps in to play detective, figure out what went wrong, and bring the system back online the right way. Remember that fault code it generated? Well, that acts like a roadmap. It tells the technician exactly where to look. One code points to that classic timing fault we've been talking about, but others can pinpoint totally different issues, like, hey, the reset button is stuck, or someone tried to restart this thing in the wrong order. This lets them find the root cause and fix it fast. And getting the machine running again isn't just a matter of flipping a switch. It's a very deliberate 4-step process. First, the tech has to actually find and fix the physical problem. Then, they have to prove the safety device is working again by cycling both channels back to their safe state. Only after that can they send a manual signal to reset the fault and finally get the machine ready to go again. There are absolutely no shortcuts. The RIN instruction is just such a brilliant example of a simple idea, the idea of self-checking, being used to build profound trust into really complex systems. It's a digital watchdog that literally never sleeps. And that kind of leaves us with a bigger question, right? As our technology gets smarter and more autonomous, how else can we design these systems to check themselves, to be their own watchdogs, and to really earn our trust to keep us safe?